So anyhow, mafic igneous rock is made up of some black stuff and some green stuff. Oh, we didn't talk about this one. A plagioclase is basically a type of feldspar, okay? And it's a dark feldspar, kind of like labradorite. Remember labradorite? All right, it doesn't have that shiny blue flash to it. But I could give you a name, but do you really want another mineral name right now? Yeah, I didn't think so. So anyhow, we're just going to call this a dark feldspar. Augite, which was black, blackish green, really. Amphibole, we said, was hornblende, which was black. Olivine is a darker green color. So again, we got a whole bunch of dark minerals over here. I didn't acknowledge it just a moment ago, but these were all on the light colored table. Remember your mineral tables? Okay. Felsic igneous rocks tend to be light colored. Mafic igneous rocks tend to be dark colored. Just a little hint for later. Which leaves us with intermediate. Gee, what do you think intermediate is, being right in between felsic and mafic? Yeah, it's a blender, it's a mixture. The big difference here, and we're going to talk about this in a moment, is this pink swathe that goes across the middle here. All right, and when we talk about this in lab, I'm going to lie to you, and I'm going to tell you that you got some dark feldspar. Where'd my mouse go? Some dark feldspar and some light-colored feldspars. Okay. In reality, there's this spectrum, this blending going on here. And you could get an entire doctorate in plagioclase. It's insane how many different minerals types are in there. And we don't really fuss about that so much. But what we do instead talk about, again, is the fact that your diorites and your andesites, those are rock names, by the way, up here. Okay, all across here are rock names. But your diorites and your andesites are going to be a blend of light-colored minerals and dark-colored minerals. So we told you that mafics were mostly dark. We told you that felsics were mostly light. So the intermediates, the one in the middle, is going to be just that. I'll tell you, diorite Dalmatian in lab. That should be your black and white speckled rock. Andesite, because it is a fine-grained, see that? The fine-grained version of this rock. Well, that black and white blends together because you can't see. Remember, fine-grained rocks, you're not supposed to see the individual crystals. So that blends together and you get sort of a gray rock. Anyhow, I'm jumping ahead, stuff you don't need to know right now, but it is all connected and it is kind of neat. So, 3 chemistries: a felsic chemistry, a mafic chemistry, and an intermediate chemistry that we recognize in this class. These arrows down here just kind of give you some generalizations about the chemistry. Felsic igneous rocks have a lot more silica content than the mafics. But that being said, if you look at every single one of these mineral names in here, or at least the translated mineral names that we gave you, and we're all in what group? That's right, they're all silicates, okay? But we're just saying that these guys have even more silica content in them than the others. Also, increasing potassium and sodium as we move towards felsic, which, again, you don't need to worry about. And as we move towards mafic, more calcium, iron, and magnesium. You see your ferromagnesiums here. That's your iron and your magnesium right there. So what it's saying is your pyroxene, which is your augite, your amphibole, which is your hornblende, and your olivine. If you went and looked at those formulas, you should see some iron and some magnesium in them. I myself don't have the formulas memorized. I'm hoping, as we say that they actually do. All right. So, again, you don't need to memorize this table. This is attempting to explain why they made these breakdowns for the 3 flavors of igneous rocks. All right, let's change gears. And let's talk about actually making rocks. So again, just want to remind you that terms lava and magma, all right? And again, that until these material fully crystallize, there are no minerals present. It's just elements. And as we just said, I see a little bit of repetition here. Sorry. As I just redoing this morning, and I think sometimes my brain gets ahead of my slides. But well, let me actually pause for a moment. Huh. Well, I dare say that this slide is redundant. How did I do that? All right, well, I'll sort that out afterwards. I may get rid of a couple of those slides. I'm not going to use up any more of your time here. So this is where I had intended to go. All right, so we want to talk about crystallization. So we're going to start by talking about melting. What? Where's the connection, you're wondering? Oh, well, I'm sure you could figure that one out. And if not, hopefully I'll explain the connection here in a moment for you. So rocks melt at a variety of temperatures. I just picked two here. Granite melts at about 625 degrees Celsius. And basalt melts somewhere over 1,000 degrees Celsius. Now, I don't want you to memorize that. I just want you to see that two different rocks that you're going to become very familiar with happen to have very different melting points. So what is the point? Well, the point is that melting and crystallization are very close, very similar, two sides of the same knife blade, if you would. What am I talking about? Well, let's talk about something we're all very, very familiar with. Ice and water. Water freezes at what temperature? Good. Hopefully you all said 32 degrees. Okay. Fahrenheit. Some of you might have said 0 Celsius. That's fine as well. But we're going to keep it in Fahrenheit for most everybody here. So water freezes at 32 degrees. So we could say that that is water's crystallization point. You follow? Well, let me ask you this. At what temperature does ice melt at? All right. A little trickier. Some of you might have just said 31 degrees, but is it really 31? Is it 31.9? Is it 31.999999999? Is it 32? And 32.1 is technically the crystallization. And again, we don't need an exact number, but hopefully you see my point. All right? As one stops, the other begins. Very, very thin, fine line here. So let's bring it back to granite. Granite melts at 625 degrees Celsius. So at what temperature does granite start to crystallize at? That's where we are. That's where we are. So what we have to realize is that we're cooling down a mixture. All right? We've got magma, we've got lava. It's already really, really, really hot. It is totally fluid, molten. All right? And we want to start growing crystals. So what we're doing, we've already way surpassed the melting point, presumably. We're cooling this mixture down, and we're starting to approach the crystallization point of these minerals. Now, a gentleman named I always jokingly say Bob Bowen. I forget what his first name was. Professor Bowen, long time ago, realized that as a lava, we'll assume he looked at a lava, not a magma, right? As a lava cooled, time after time again, the crystals started to grow in the same order. First this would grow, then that would grow, then the next thing would grow. And he did this time and time again. And, you know, there's 3 types of lavas. We're keeping that in mind. And depending on the type of lava, you would see this predictable series. So this came to be known as Bowen's reaction series. Okay? We're going to spend some time talking about this. You could write out the word Bowen's reaction series all you want. I tend to abbreviate it BRS. Where's my mouse? BRS. Okay? That's going to be the tagline for this semester. Where's my mouse? I'm sorry I say that so much, but it really does disappear very quickly on my end. So what this shows us, first and foremost, is that not all minerals crystallize at the same temperature. You just can't take a thing of lava and wave a magic wand at it and cool it instantly, and all these crystals grow. First, something's got to grow first. And then as it continues to cool off, something else will start growing. And then as something cools off, as that starts to cool off, the next thing will start growing. This is temperature based. Okay? And it's just worth knowing, I don't mean to confuse you with this here, but just, again, something to keep in mind. Minerals with higher melting points crystallize before minerals with lower melting points. Remember, melting and crystallization are the 2 sides of the same coin. You follow? All right. All right, so Bowen's reaction series. We're going to look at the diagram in a moment. What I'm going to draw your attention to is that there's 2 portions to it, a discontinuous branch and a continuous branch. And I don't want to say the one that's going to make the most sense, but the one that's easiest to explain is the discontinuous, and because it has unique, distinct stopping points and mineral names in it that you recognize. The continuous branch is that spectrum I was talking about earlier, that swatch across the center. Let's just go to it. All right. So again, what you want to keep in mind here is that this is a molten material. It's super hot, and we're cooling it off, so our temperature is decreasing. And what we want to think about is what's the first mineral that's going to grow? Okay? What's the first mineral that's going to grow? So I'm just going to use made-up numbers over here with this. Where the hell's my mouse? There it is. I'm going to use made-up numbers over here, and we're just going to say this starts at 5,000 degrees, okay? So this magma's cooling. All of a sudden it hits 5,000 degrees. It starts to grow or crystallize olivine. All right? That goes on until, again, just making up a number here, it cools off to 4,000 degrees. At 4,000 degrees, it stops making olivine, and it starts making augite. Remember, pyroxene is augite. And then at 3,000 degrees, it stops making augite, starts making hornblende. At 2,000 degrees, it stops making hornblende, starts making biotite. You dig? All right. And then at 1,000 degrees, it starts to make your orthoclase. And then the last thing to grow is quartz. That's the first half that you need to understand, okay? Don't worry, I'm not going to ask you this order. I'm not going to say, which of these is in the correct order of sequencing for Bowen's reactions? I don't care about that. If you're going to go on to become a geologist, yeah, you could worry about that then. Right now, I just want you to know that there is an order, okay? And it's predictable every single time this will grow, as long as you have the right ingredients. And that's where I want to go next. Okay, so let's go back. Remember, this is a pool of elements, right? What's in olivine? Yeah, I don't remember either. But we can almost be guaranteed that there's some silicon, some oxygen, some aluminum or some iron in there, right? So whatever it needs to form olivine, it's going to pluck those ingredients out of the mixture and lock them up into those crystals. Can't use them anymore. You've grown olivine out of it. I usually use a baking metaphor here. You've got your cupboard in your kitchen with your flour, your sugar, your baking soda, your chocolate chips in it, whatever. Okay? So you say, okay, let's have a bake sale and raise funds for our club on campus. Okay, fine. Here's our ingredients. Let's start using them. You bake your first batch of cookies, and you used up this, that, and the other thing. Next, somebody says, oh, I want to start making brownies. Okay, well, do we have enough flour and sugar left? Yeah. Oh, but we need to pull in some cocoa this time. All right, you look in the cupboard, and okay, you use up your cocoa. The point being is by the time you get further down here, you might have used up some of whatever you need to make biotite. Again, you don't need to memorize these formulas, but understand the idea that there are formulas. There are certain things that you need to make biotite. And you know what? If you don't have that ingredient, you're not going to make biotite. So what happens? Well, believe it or not, it doesn't make anything for that time being. And then when it gets down, you see muscovite in here. Okay, I kind of skipped over that earlier. Let's say it didn't have whatever it is that makes biotite unique from muscovite. It doesn't make anything here, and when it gets down to this temperature, muscovite starts to form, along with your orthoclase and your quartzes, eventually. And it's also worth noting, you all hopefully know what's in quartz, right? You only got two ingredients. It's the simplest of all your silicates. You got silicon and oxygen, the two most commonly occurring ingredients, and guess what? That's the last one to form. So once everything else is gone, that's all that's left to grow. Pretty neat, huh? So the discontinuous branch, we call it discontinuous because it stops making one and starts making another. All right? And it's temperature based. Now, the other half of this diagram, the continuous branch, this is that weird Feldspar spectrum I was telling you about. And again, it is temperature based. So we start to grow those dark feldspars first, kind of like the labradorite stuff. And then one of the last things to form is that sodium-rich, the albite. Okay? And in between, there's 1,000 different ones in there. And it just blends from one to another, to another, to another. Eventually, you get something rather distinct when you look at the two ends. But that area in the middle is tough. So that's why we sort of fib to you in lab about there just being black and white when really there's an awful lot of gray. So we don't worry too much about this one. Okay. But this discontinuous spectrum, as I said, hopefully made some sense to you. And it's worth noting, this diagram is actually a sort of a flipped version of the one we've been looking at. If you take this silicic here, felsic, and put it up over here in this corner, which puts mafic right here, these minerals line up underneath it, and it looks just like that other diagram, kind of. It's all connected, man. It's all connected. All right. So, switching gears again. And this is why, I tell you, when you read the book, you're going to come across some stuff that I don't talk about in lecture. All right? And that's fine. Don't just skip it. Read over it. But when it starts to say, wow, I don't remember him talking about this, don't get nervous. Check your notes. Make sure we didn't talk about it. And then don't worry about it. I'm never going to test you on something that we don't talk about in lecture. So as you read in the textbook and you see some stuff, you know, feel free to ask me questions about it, but don't get real nervous that oh my gosh, I have to learn that for myself. No, I purposely sort of edited it out, if you would. All right, I edited it out so because I felt that you didn't need that bit to understand the important stuff. So, anyhow, do read along though. We're changing gears, as I said, and moving on to igneous intrusions. There's two types of igneous rocks, right? Your intrusives and your extrusives. Extrusives get their own chapter because they are basically volcanoes, volcanics. And that's what we're going to do the next chapter. So we kind of stick intrusive igneous rocks into this discussion. A couple slides on it, done and done with it. And then, like I said, we've got an entire chapter, a lot of conversation about volcanoes. You guys find volcanoes much more interesting than this, understandably. So, intrusive igneous rocks. Magma works its way up towards the Earth's crust and enters through cracks. The crust is old, right? We know about plate boundaries, and gosh, there's all kinds of other cracks all over. You've heard of earthquakes and stuff, right? So the crust is old and cracked. That magma in the mantle, it's under pressure. So wherever it can find a way to ooze in, it does. And oozing in, well, how about intruding? Intrusive igneous rocks. Igneous intrusions are what we're talking about. So, anyhow, it's cooler in the crust than it is in the mantle, so slowly but surely that material begins to harden, turn into rock. But not before it doesn't, not before it flows all through it, right? Not sure why these are needing extra clicks to show up there. We recognize three types of igneous intrusions in this class. We recognize dikes, sills, and plutons. Dikes, sills, and plutons. A dike is an igneous intrusion that is discordant to the bedrock. A sill is an igneous intrusion that is concordant to the bedrock. And don't worry, we'll tell you what that means, but you're familiar with discord, right? Is discord in music or in life, is that something that's pleasant? No, it's harsh and cutting, right? So discordant, that means it's going to be cutting through the bedrock. Concordant, con actually means with. So a sill would go with the bedrock. But again, as I said, we'll spell that out a little later for you. And then a Pluton. A Pluton is a large pool of magma or lava. I'm sorry, of magma, really, since we're inside the Earth. And that fills up, and oftentimes that's what ends up feeding your dikes and sills. But sometimes just, you know, it just fills up and it becomes a igneous intrusion in and of itself. But I usually use it as the feeder when we draw diagrams and we talk about it, that the Pluton fills the dikes and the sills. And speaking of Plutons, before we go any further, you're going to see laccolith, batholith. There's another one too. His name just jumped out of my mind. Those are all variations on the same idea, pools of magma that build up. We're just going to keep it simple right now and just going to refer to Plutons, okay? So when you see laccolith, I didn't delete it from here, so I'd remember to mention it to you. But when you see laccolith and batholith, again, just smile and nod. In here, we keep it simple. We got Plutons, sills, and dikes. So, remember I told you that we had the words discordant and concordant. Those are relative terms, right? With the grain and against the grain, to borrow some woodworking words. It's best to think of, it's easiest to think of, horizontal rock layers. Okay, what's going to be your sedimentary rocks for the most part are going to be flat or horizontal. In that context, oh, excuse me, yawning. In that context, sills are horizontal, while dikes are vertical, or mostly vertical. You see this one's going at a bit of an angle, but I didn't say perpendicular, right? We said vertical. So sills are going with the grain. Dikes are cutting across the grain. And if you are looking at these like pipes, that's a good idea, okay? Little feeder pipes. Starts with this Pluton and it works its way through cracks. And when it can, it spreads out to the left and to the right. It keeps flowing, spreads out again. So that's really all there is. All there is to it. The Pluton is a big pool of magma. The dike is a vertical escapee here. And then when it spreads out to the left or to the right, it's a sill. We've got some actual images here for you. Crazy, huh? See this dark area that looks wet? All right. That's a igneous intrusion there. Literally cut right through this existing. See how these rocks are all layered horizontally here for the most part? It cut right through there. This is long since eroded away, weathered away, whatever word you want to say. Weathered would be weathered and eroded, really. So boom, okay, cut right on through there. A sill, it's right here. Boy, that one couldn't be more straight, could it? Couldn't find a picture of a Pluton. They had several. Well, actually, Pluto is apparently Pluton in another language, because when I Googled images of Pluton, I got many images of Pluto. But there were a few rock pictures in there as well. And they were basically, because igneous rock is so hard, it doesn't wear away very easily. So there are these big round mounds in these flat areas, and those were weathered out Plutons. Not exactly, I was hoping to find one sort of in situ like we have here, or here, you know, surrounded by the local rock or the bedrock. All right, I use the word bedrock a lot. I haven't really defined it. Bedrock is the local rock, the country rock, if you would. The usually sedimentary, okay, because for 4.5 billion years we've got so much sediment built up on top of everything else. But so that is the local, the area rock. It's the hard rock underneath all the soil and rubble and all that's there. All right. So that's what bedrock is. At any rate, so we got I couldn't find a Pluton in some bedrock. I apologize. So, back to really what that diagram showed us a couple minutes ago, and I did not acknowledge. If there's enough magma and pressure, that pipe works can work its way through and poke out at the surface and erupt. We call that a volcanic event. And as I indicated a few minutes ago, volcanoes get their own chapters. So that's where we'll be heading next. Any questions, feel free to email me. Take care, folks. Have a great day.